Okay, this is where we left off last lecture. So we had calculating, I zoomed out so we could see, calculating what these coefficients C sub n were if we have, this is the state we prepared our system in. So we prepare our state in this psi of x0 is just a triangle wave, as illustrated there in red. And then we're saying, what combination of the steady states are we in to have that starting state? And so we went through using this equation here to calculate what the amplitude, let's say, for each of the different steady states is. And so we're most of the way through the calculation. We had, I'll put a box around this equation, maybe. Okay, so we had that equation that we're trying to resolve to find what the Cn is. And so I broke it up into three integrals. We did the, oh wait, that's the wrong one. No, it was the right one. Wait, let's undo the undo. So we broke it up into three integrals. So I did the black integral, and we got to our end result here. Did the blue integral, got to the end result here. And now all that's left is the green integral. So we'll do the green integral. Which is thankfully the easy one of them all. Got to divide by that thing. I didn't give myself enough room. So the integral of sine is minus cosine. And so then putting in our limits, there's a minus sign out here from the integral being a minus cosine, so don't forget that. I still have it on replacing shape, so it made that into a box. So the second one's going to be plus because it's minus a minus. So there we have all of the terms. Now we have to add all of these terms up, remembering that it is going to be square root of 24 divided by, was it L squared? Yes, the number there that's in magenta, times the first one minus the second one plus the third. So the first one we have then going to the second one. So the blue one. What was that?
I was just trying to, see if anything canceled out. I forgot.
They all but one will. All but one will. I did it this morning and it worked the first time. Had to work eventually.
That's right.
Okay, so going to the blue one now. Notice that I changed the sign because it's minus the blue one. So instead of a minus sign, that became a plus. Yeah. I'm going to move this. I'm rearranging to match what's above. And then the last one, oh, I wrote that one in the wrong place though. So there I have the three terms from the blue one, all of them with the signs reversed. And I've aligned them so you can see the first two are the same. They're going to add up. The second two are the same. They're going to add up. The third one was different. And then finally, the last two back to plus. And so cosine of n pi over 2 over 2, and then minus okay, so I probably need a bigger bracket. I mean, by probably, I mean I definitely need a bigger bracket here. So there we have it. And as you can see, this column here adds up to 0. Because the first two were over 2 and negative. The last one didn't have the over 2 and it was positive. This column here adds up to 0. And this column here is L squared over n squared pi squared 2. So I'll put the 2 out front. Sine of n pi over 2. We can't forget that we had the square root of 24 over L squared. So we're going to have the L squareds cancel. And we have, in the end, coming all the way back, Cn is equal to 2 times the square root of 24 over n squared pi squared sine of n pi over 2. Right, just going back to make sure I copied that right. Sine of n pi over 2, n squared pi squared on bottom. So now we can calculate all of the C sub n's for every n. What's the first thing that stands out to you? Can you see a pattern in this?
It doesn't depend on L.
Okay, it doesn't depend on L. That's correct. What happens if you have n is, let's say n is equal to an odd number? It's going to either was the right word.
Yeah. It's going to be either 1 or negative 1.
Okay, it's going to be either 1 or negative 1
Well,
times the stuff out front. The sign term will be either 1 or negative 1. What if n is an even number?
then it's 0.
Then it's 0. So I made a little where is it? A little Google Sheets where I just calculated it. That number out front, actually, this is without the 2. Or is it with?
Mm-hmm.
I don't know. Anyway, these are the CNs. The n equals 1 state, it's 0.99274 to that many decimal places. Almost 1. The n equals 2 is 0. The n equals 3 is 0.11030. 5 is 0.0397096. I went out to a pretty high n. What's the point of this? The sum of all of my CN squareds is approaching 1.
Mm-hmm.
It should. Why should it approach 1?
your slides.
Absolutely.
I'm drawing a blank on what C events or CNs or
They're defined on the slide here.
yeah, there it is.
The CN is telling us how much of each state.
All space shouldn't all of our spaces equal 1? Like when we normalize all space.
That's the key. It has to be normalized. Now we normalize each one of our steady states, but if we do the integral of our full psi star full psi dx over our entire space, which is just 0 to L, that has to equal 1. Now the whole thing has to be normalized, not just each of our individual steady states. And so if we do this, because of the orthogonality, because psi n is orthogonal to psi m unless n is equal to m, when you do this, what it's going to turn out to be, I'll just do it long way. So this is the individual steady state. Just to be consistent here. It's not going to be very consistent because I missed the 0, but I think we can, I'll just erase this. Okay, so there is our normalization, or that's what we have with psi star psi. That's got to be equal to 1.
Right.
But because of our orthogonality relationship, didn't give myself. When I rearrange it like this, since n, m, and the c's are not functions of x, I can easily pull those out. This here has to be equal to that Kronecker delta mn. And since that Kronecker delta mn is there, then I can collapse one of those summations because I have to have m equals n, otherwise it's 0. And so that's equal to sum over n of c sub n mod squared. And so the sum of those mod squareds has to be 1 because of our normalization situation.
Right.
Now, I told you last time the c sub n has some meaning, and I was going to say, and I was like, I better read up on it so I don't misspeak. And it's good that I did, because if you look on the textbook, which I didn't bring, of course, it says, now what do these, it's a footnote. What do these mean? Many people say that the c sub n tells you the probability of being in the end state. But that's using poor language choice or bad wording or something like that. And goes on to say what it really means is the c sub n mod squared is the probability that if you make the measurement of energy, you'll have the end state energy. So it's not so much that you're this percent in this state. It's that if you make a measurement, you have this probability of measuring that energy. It seems very much like the same thing, but one's much more precise to what it means than the other. So I'm glad I didn't blurt it out before reading up on it on Wednesday. So this exercise that took pretty much all of last class period, the beginning of today, what's the point of it? Right? Obviously, I don't do an exercise for no point, but when you go so long in an exercise, you kind of forget what was the point.
Yeah.
So the point was to show that indeed we can find what these coefficients are, so I can write out my equation, my state that was the capital psi of x comma 0 is what the function of x was, is the sum over n of each one of those c sub n's times the steady state solution n. And because we chose a state that has a lot in common with the psi 1, that is, psi 1 is an upward arc, and we had a straight thing like this, it was dominated by that. It was over 99% that. And then the other things were straightening it out to make straight lines on the way up and down. So what we have now is it's a linear combination of all of the odd steady state solutions that we excited by that. The reason I chose this function is because it's like Indy playing his bass guitar. If you were to pluck the string at the center, you would get primarily the fundamental frequency, right? The psi 1 in this case. But then you have all of these overtones, only the odd overtones that are also excited. So the wave on a string analogy is very strong here, much like the force. Right? Watch it. All right. So that's why we did it. We've now seen breaking it into, we've taken something that's fairly realistic, except for we're talking more about a wave on a string and how we could prepare the system. Any questions before I move to the new topic of classical harmonic oscillator 2.3?
No.
Now, I am going to put in some homework this week. The homework will be mostly on the particle in a box, with also a little bit on this harmonic oscillator that we're going to be talking about for the rest of today and also on Monday, so you have 2 days worth to cover that.
Okay.
So you guys have both taken college physics, probably taken modern physics too, right? So you've studied the harmonic oscillator. Harmonic oscillators, we tell students in general physics, here's your definition for a harmonic oscillator. You have to have a restoring force, minus sign, so it's restoring, that's proportional to the displacement. And right away you say, okay, what makes that? A spring makes that. A spring has exactly that equation that's in the box, Hooke's law. And so this is very applicable in general physics. But then in general physics, we say, are there other situations where this is useful? Do you remember a discussion like that?
Yeah, a little bit.
Do you remember other situations? Do you remember other situations where this is useful?
Atoms, and like the bonds between atoms.
Okay, in the bonds between atoms, it's useful. Now, is the bond between atoms, strictly speaking, a spring following this minus kx? The answer is pretty clearly no, otherwise I wouldn't have stated it that way. But to a good approximation, it is. In fact, anything that has a curvy shape, if you take the bottom of the curve and you zoom in, okay, zoom in, and you zoom in enough, in the small region around the bottom of the curve, it's going to be something that you can model as to a first order approximation obeying this rule. Now, if you get farther away, this rule might go like this and on one side and like this on the other, and you're like, okay, well, it clearly diverged if I got outside. Oh, that was not a wise choice. It clearly diverged if I got outside of this box. But inside that box, if the amplitude is small, so it stays within that box, it's behaving like a simple harmonic oscillator. So that's why we talk about it when we talk about chemical bonds. As long as they're not vibrating too much, we have small vibrations, it's going to behave like a simple harmonic oscillator. So this is now getting to a really real situation. It's something that for small oscillations, just like if you're in a swing, for small oscillations, it's a simple harmonic oscillator. Large oscillations, it's not. And so for those special situations of small oscillations, which are very common, this is truly applicable. So we've gone from something that is kind of realistic to something that really is applicable here. Now, this one slide is my entire slide for the classical solution. The classical solution says that the position of a simple harmonic oscillator is going to be a sinusoidal solution. I put it here with a sine and a cosine. You could have put that as another amplitude, C time, let's change to a thicker pen. C times sine of omega t plus phi. That's equivalent as well. Still two constants, the amplitude constant and the phase constant. So they mean the same thing. And the angular frequency, omega, is just the square root of k over m, where k is the spring constant if it's a spring. It's the constant for the force that is restoring, and no matter what your situation is. So different situations, you'll have different physical things that k is representing. And then over m, the mass of the oscillator. And the total energy is the total energy stored in the springs, which is 1/2 k times a squared plus b squared. Or if I had done it this other way, it'd be 1/2 k times c squared. And then we can write, because of this relationship, if I square both sides, I have omega squared is equal to k over m. Therefore, k is equal to m omega squared. And so I could rewrite k as m omega squared. And once again, any right-minded person says, why do you want to do that, Richard? Why? It was perfectly fine to have k instead of two different letters, one of them having a square. And the reason is because we're setting the field for going into the quantum physics solution. So that's our classical solution. Now, if you take classical dynamics, you'll learn about normal modes, and you'll do a lot of fun work with this. I'm guessing you haven't taken that, is that right? Or, I don't know, dynamics, might call it mechanics. Yeah. It actually is a totally fun class. You get to use the Lagrangian, and you figure out, wow, this is actually a really simple way of doing a lot of hard problems. That made me really happy to know there was a simple way to do a hard problem. Okay, so let's go to the quantum one. For the quantum oscillator, we have our potential energy function that is the potential energy of a spring, right? Simple harmonic oscillator, spring, 1/2 kx squared is the potential energy. And once again, using that substitution, that's 1/2 m omega squared x. So that means our Schrodinger equation we have here is our kinetic energy operator, our potential energy operator. I'm going to use the Curies today for operators because it'll save me a lot of writing. Equals my energy eigenvalue times the wave function. So there's my Schrodinger equation. And my Hamiltonian, which is my operator for the total energy, is kinetic energy plus potential energy, can be written as, well, you know, kinetic energy operator is P operator squared over 2m. And so Hamiltonian is kinetic energy operator plus the potential energy operator and so that's what we have here. Potential energy operator squared over 2m, and then the 2 here is getting rid, oh my goodness. I am pretty sure I made a mistake there. Oh no, I did it right. Hey, yes, there's a square outside. I was like, that doesn't, yes it does. So this is writing the Hamiltonian operator. So the Hamiltonian is the left side of our Schrodinger equation. Hamiltonian acting on psi is E psi. Now comes what I consider a true walk on the wild side. I wrote here, using mathematical trickery. The Hamiltonian can be written as, we have to first define these two new operators, A plus and A minus. And this is where, when I was taught this, I was like, why? Why would I want to take a pretty simple looking Hamiltonian and make this crazy complicated new operators? And of course, when you get to the end, then you see the why. And then I say, what kind of genius came up with this idea? Because I would have said, would have been it. So we define the A plus operator as 1 over square root 2 h bar m omega times minus. So notice with the plus comes a minus. Opposite signs. And immediately you're going to be like, why do you have the opposite sign? Why, good sir? And it's because of what the meaning of the A operator turns out to be. So minus I P operator plus M omega X operator, and A minus is plus I P operator plus M omega X operator with the same thing out front. I know, it just looks foolish. And before we go any further with that, we have to talk about a new thing. And this new thing is going to be definitely problems you're going to have in the homework. The commutator. The commutator really is an important idea. Have you guys did you do commutators in your modern physics?
I don't remember the name, no.
Okay, don't remember the name. Works for me. The commutator is defined as, and believe me, I redid this equation to make sure the bracket had the top on it because I'm that kind of anal. It's still not there. I redid it just to make sure. It looked right. So the commutator is defined with this notation. That notation of bracket, operator, comma, operator means the commutator, and the commutator is the first one operating on the second one minus the second one operating on the first one. Now, if these were numbers, if I had 5 comma 7, the commutator would be 5 times 7 minus 7 times 5. And we're all really smart here. We know 5 times 7 is equal to 7 times 5. Now, with the new Common Core math, they will tell you that it's slightly different. One of them is 5 groups of 7, and the other one's 7 groups of 5. Never once in my life have I thought of it that way, but that is one of the things they're trying to emphasize with the new Common Core. So people can get marked wrong if they show 5 times 7 by bundling the wrong number. That's the kind of thing that gets people annoyed. Just to go off on a tangent, you guys know about Common Core math, right?
Yeah.
You've probably heard a lot of people moan about it, right?
Yeah.
Apparently. Common Core math at its core is trying to take the tricks that we learn as we become adept at math and trying to teach those tricks before they learn to do the real math. I think it's folly because the tricks are worthwhile tricks, but you need to fundamentally learn what you're doing before you start applying tricks to it. Okay, so enough of that. Let's get to commutators. The first commutator we always do is X operator. Okay, let's move off of the edge of the slide. X operator, P operator. So by definition, what is the commutator of X with P going to look like? How do I expand that?
So it's going to be X times the
Yeah, I say you can go short. You don't have to go long.
Yeah.
And then,
P operator times X operator.
okay, make sure you remember the minus sign. P operator, X operator. Now, how do I evaluate this? To evaluate it, I know that was a rhetorical question. To evaluate this, we make some magical who cares wave function. So to evaluate this, I throw in a psi here. And you're like, if you're a reasonable person, you say, why? Well, I'll show you why.
Operator. Give me the operator.
Okay, so the X operator acting on psi gives me X times psi. So I drop the operator sign. Yeah. Now, if we take this, we can go ahead and do our math. The left term, x operator acting on this function, I don't care that it's a new function. The x operator is still going to return x value times the function. So this left one is just going to be the x value times minus I h bar d psi dx. Now the right one, we're going to have to use the product rule. Now it's a minus and a minus, so I'm going to use the plus signs. And it's going to be plus I h bar. Using the product rule, the derivative of x psi is going to be just psi plus I h bar x d psi dx. Now, do you see something fun? Yes, I do. Sí, señor. Class that was before us here. What's this going to simplify down to?
X plus I h bar psi. That's if I can't read. So it's possible. No, there's an x there too. Never mind. It's just I h bar psi.
Yep. Those two add to 0. So the commutator of x and p acting on psi gives me I h bar psi. This commutator is itself an operator, and apparently the eigenvalue for this operator is I h bar. And so our commutator is written then the x Now you're going to do fun things like find the commutator of the Hamiltonian with the x operator, or the Hamiltonian with the p operator, or some random operator that's made up with some other random operator that's made up. But being able to do this commutation thing is very important. If the commutator is 0, a terminology, we say that the two commute. And what that means is they share the same set of eigenstates, eigenfunctions, the same set of steady state solutions, right? Because we haven't really talked about the terminology of the eigensystem. So using those terms is a little bit troubling. But they share the same solutions. And you can freely exchange the order in that case. So if they commute, you can change the order. If they don't commute, you have to be very careful with the order. If they commute, if it's equal to 0, they will have they are simultaneous states. They'll both have the same states. You'll get an eigenvalue for each. You will have no uncertainty relation if they commute. If they don't commute, you're going to have an uncertainty relation. And in fact, the actual uncertainty relation, going from the Heisenberg uncertainty to the generalized uncertainty relation, involves using the commutator. So when we get to chapter 3 and look at the uncertainty relation again, we'll look at the commutator as how we're determining the uncertainty relationship between any two variables. So I know it seems like that was just an unrelated soliloquy, but no, this was necessary because what we're going to do is we're going to say, what happens if we make these two operators act on each other? The A minus and the A plus act on each other. And so here is my A minus. Notice it's got the plus sign. And here is my A plus. And we notice right away they both have that same 1 over square root of 2 h bar m omega. So we can bring that out as just a regular 1 over 2 m h bar omega. But then the order matters. Momentum and position do not commute. So I can't just exchange their positions. So I can't do this the way you normally would. You have to always have the operator that is in the first one here is the first one when you're multiplying the two binomials. Is binomial, right? And so you have the IP operator times minus IP operator. Well, that's just going to be P operator squared. And then IP operator on M omega X operator, which is going to be, well, that's this one. That's this one. I M omega P first, then X. So this here is the one that I underlined in blue. Then when I do M omega X operator acting on minus IP operator, then I have minus M omega X first, then P. Right, so these two do not add to 0 because the X and P are in opposite orders. And of course, yes. And so the next two steps are just rewriting this, bringing the two H bar M omega in over here. So you have the M omega cancels, you just have over 2 H bar. And then XP minus PX, which is the commutator that you just said. And so you replace that commutator with I H bar and minus, excuse me?
Quick question.
Yeah.
Is on the second term, the M omega X operator squared, is the square supposed to be on the outside of the parentheses?
I rewrote it this morning, and I thought that I was.
Isn't that the term M?
Yeah, no.
X operator times?
It is supposed to be on the outside. You're correct. It's supposed to be out here. I saw that this morning and rewrote things. I'm not sure what happened if I saved the wrong version, which could explain why this here didn't have the top of the brackets as well. I might have saved the wrong version because I noticed, yeah, who knows what I did. Because I was pretty sure that I actually separated that into this being P operator squared over I thought I'd split it out. So I think I saved the wrong version. Always embarrassing, but we go on.
Yeah.
Why did I get up and work on this in the morning, you wonder? Okay, so the right-hand term then, if we take minus I over 2 H bar and multiply it by I H bar, the commutator value, that's equal to minus I times I is minus I squared or plus 1. H bar over H bar cancels, and that's just 1/2. So what we have here is a minus operator, a plus operator is equal to 1 over 2 H bar M omega times P operator squared plus M omega X operator all squared plus 1/2, which allows us to rearrange. And I'm going to show the rearrangement. Yeah, I've got room here. Well, let's expand this first part. So notice the P hat squared over 2M is kinetic energy, so I'm going to leave 1 over 2 H bar not factored out, or actually still factored out, and only bringing in the 2M This one I'll do more explicitly, especially because of the incorrect, yeah. I'm pretty sure I had this page different too. I brought in the 2. It's the H bar omega that I didn't bring in. So now I can cancel one of these M's. We usually put the H bar first. The Hamiltonian operator was P squared over 2M plus 1/2 M omega squared X operator squared. So this is the Hamiltonian. Well, now that we found this, we just solve for the Hamiltonian. So any kind of genius says the first thing I'm going to do is subtract 1/2 from both sides and then just multiply everything by H bar omega. And what we have is the Hamiltonian is equal to H bar omega, A minus A plus, minus 1/2. So here I've written the Hamiltonian in terms of these A minus and A plus operators. Hence this equation. Now that's not the only way I could have done it. I could have used A plus A minus instead of A minus A plus. That would have made a difference, right? So I'm not going to go back and completely reinvent the wheel. I'm simply going to point out if I change the order of these two, it would have changed the signs of those two. The signs? I would have had, yeah, because I would have had the negative IP in the first one and the positive IP in the second. And so I would have had the one in blue would have been negative and the one in magenta would have been positive. So that means that if I had reversed the order, it just would have, in the end, changed the sign of the 1/2. So I also could put now that's the shortest way to get there. I could have also done the commutator of A minus A plus with A plus A minus. By comparing these two, you can actually see what the answer is to that. But I think that's going to be one of your homework problems, is to find the commutator of, like A minus with A plus and so on. So I don't want to ruin your homework problems. Got to have practice with your commutators. So the Hamiltonian can now be written in terms of these new crazy functions that we defined for no apparent reason, right? In terms of these two new operators. And so the question becomes, what have I bought myself? What have I done that's been valuable? I've done a lot of algebra, but why is that valuable to me? Yes, this is definitely the wrong one because there were 3 more slides as well. Excellent. Well, you have your textbooks? I know I saw Chris's. This is getting near the end of, I of course don't have mine, but near the end of 2.3.1. Yeah. And the next one is, what is the Hamiltonian acting on A plus psi. And I think it's left as a problem to show that is, it doesn't say it's left as a problem. Well,
yeah, it shows that it satisfies the Schrodinger equation with a certain energy, and then it gives a proof why that's true.
Yeah. If we take this H acting on A plus psi, that's going to be with this new operator. And I'm going to use the second form. So this is just expanding. This is my Hamiltonian. And so here I've rearranged that relationship where I have the A plus operator now I've put here, taken it away from the psi and put it with my operator. And then we look at this and we say, well, what is A minus A plus? If we do the commutator between A minus and A plus, or A minus A plus and A plus A minus, I'm out of time, so I don't have time to do that commutator, but that gives me a substitution that I can use for the A minus A plus. I'll have to pick up here next class period. I suppose it didn't matter that I didn't have those slides, but yeah, you have confirmation that yes, I used the wrong slides. Did I have something wrong there, Chris?
No, I'm still trying to think of the question.
Okay, so kind of where this is going with it, I can't help but notice the figure on the next page.
The ladder?
Yeah. So is this leading us to how to find energy solutions?
Well, it actually is going to lead us to finding everything. What we're going to find, and actually, the third slide of the three that's missing had the energy and the wave function, because you get to the what we find is that the A minus is a lowering operator. It lowers the energy by one energy state. The A plus is an energy raising operator, raises the energy by one energy state. And so we get down to our bottom operator before you have no wave function, and it gives us a very simple differential equation, the kind that you can already solve, and you find your wave function for the ground state, and then you can use the raising operator to find all of your wave functions. Mm-hmm. And so it's an algebraic trick to making it so you can solve this. So I will pick up with this slide here. I'll use my new and improved slides to show you, hey, I could go change them now. It wouldn't prove anything. But I'll pick up here with the ladder operators next class period on Monday.
Sounds good.
All right. Have a great weekend.
Thank you.
Oh, did you have a question?
Yeah, whenever you had the Hamiltonian,
Yes.
the stretched out version times the A operator, the A plus operator times the psi.
Okay, so A plus operator. Okay, so that's at the bottom here.
At the very end, like
Yeah.
right there, the second bottom thing. How are you able to bring the A plus off the psi?
Okay.
Isn't it operating on the psi?
The A plus is operating on the psi, yes, and the A minus is operating, and the A plus is operating. What I did was I split off a different one. So if I actually, I'll make this one color. And so this is equal to A plus so I distributed that A plus over to the left. So this is that one, and this is that one. So I didn't change any order. I just rewrote how I was writing it. Except for what thing? That was a mistake. I would have had a dagger. Instead of plus, I was taught to call that a dagger. I would have had A plus the way I wrote it. So that was a mistake. Glad I noticed it.
Okay, that's
Yeah.
what I was just wondering about. I was like, wait a second.
Yeah,
that was my exact.
When I wrote it, I was thinking this isn't what it has in the book. But it seemed right. But yes.
Okay, that's much better. Okay, thank you.
Yeah.